Dear students, hi. In continuation with the e-lecture series of the course Atomic and Molecular Physics, course code PHYS 4009, today I am going to deliver a e-lecture on molecular spectroscopy. When we look at the topic molecular spectroscopy, few questions come in our mind. What is the term spectroscopy? What does light do to the molecules? How can you produce a molecular spectrum? What information does the molecular spectrum give? After we go through the lecture, what will we achieve? Understanding of how light interacts with molecules. Molecular energy states. How to use spectroscopy to quantitatively characterize molecule. How to extract molecular information. Let's start the lecture with term spectroscopy. Spectroscopy is the study of electromagnetic spectra, the wavelength composition of light, due to atomic and molecular interactions. Here you see the electromagnetic spectrum from gamma rays to radio waves. This describes the different regions of electromagnetic spectrum. When we look in these different regions, the wavelength compositions of these regions corresponds various physical processes, and depending upon that they can be utilized in various applications. Some of them are presented here pictorially. We have learned the X-rays in detail in our previous lecture on X-ray spectroscopy. The region from ultraviolet to microwave comes under the molecular regime. In this region various molecular processes occur that are electronic transitions, vibrations, and rotations. The spectroscopic study under this molecular regime is termed as molecular spectroscopy. Any molecular process occur only when there is an interaction of electromagnetic radiation with matter. The interaction causes change in the incoming radiation. Therefore, by studying the outgoing electromagnetic radiation, we can study the properties such as electronic, vibrational, and rotational properties of the molecules. Following phenomenon can occur when electromagnetic radiation interact with matter. Reflection, transmission, absorption, scattering, photoluminescence. Now we can redefine the term spectroscopy as spectroscopy is the study of matter, that can be atom or molecule of any substance, by investigating light, sound, or particles that are absorbed, emitted or scattered by the matter under investigation with the help of spectroscopic instruments. In order to study the interaction of light with matter, we first have to understand the nature of light. Light is nothing but an electromagnetic radiation. Any electromagnetic radiation can be represented by this graph. In this graph the variation of electric and magnetic field intensity is shown as a function of time on Z and Y axis, respectively. The variation of electric and magnetic field intensity can be represented by these equations. where E is the electric field intensity at any instant of time, E0 is the amplitude of electric field variation. Similarly, B is the magnetic field intensity at any instant of time, B0 is the amplitude of magnetic field variation. K is wave vector represented by, and omega is angular frequency. Nu and lambda are frequency and wavelength, respectively. Photon is the smallest quantum unit of light or electromagnetic radiation. The energy of photon can be represented as, where energy can be written in terms of frequency, wavelength and wave number. H is universal constant named as Planck constant and c is the velocity of light. Wave number is inverse of lambda in centimeter. Most of the vibrational and rotational spectrum are represented in wave numbers. When an electromagnetic radiation interact with matter, following kinds of molecular interaction occurs. Absorption. We can understand the absorption process with the following energy diagram. Here E and E' represent the ground state and excited state energy level, respectively. The energy difference between the two levels is h nu. Let us consider molecule is initially at ground state. And when a photon of energy h nu is incident on substance, molecule undergoes transition from ground state to excited state. This process is known as absorption. Now another process that occurs is emission. We can understand the emission process with the following energy diagram. After the absorption of molecule takes place and when molecule is in excited state, molecule try to go back to its ground state, in order to attain the minimum energy state of the system, and undergoes transition, after a lifetime of the state which is of the order of 10 to the power of -8, to the ground state by emitting a photon of energy h nu. This is known as emission. Apart from the absorption and emission, another process that can take place is the scattering. In this process, when photon interacts with the molecule, there can be two possibilities: that photon gets scattered, without any change in energy, or photon gets scattered by changing its energy. In the second case, the scattered photon can have energy less than the incident photon by giving some of the energy to the molecule, or in another case the scattered photon can have energy greater than the incident photon by taking some of the energy from the molecule. This process is known as scattering. Let's see what are the different energy states exists in the molecules. The molecules have electronic ground states, electronic excited states, vibrational states, and rotational states. Here you see the plot of molecular energy of diatomic molecule as function of its internuclear separation. The below curve represents the electronic ground state, and the upper curve represent the electronic excited state. The parallel line between the curve represent the vibrational energy states. The parallel line between the vibrational states are rotational states. Now, if the incident energy lies in the UV or visible region, molecule undergoes transition at specific condition from electronic ground states to electronic excited states. This type of transition is characterized as electronic transitions. If the incident energy lies in infrared region, which are not sufficient for electronic transition, molecule undergoes vibration transitions between the vibrational quantum states. If the incident energy lies in far infrared or microwave region. Molecule undergoes rotational transitions between the rotational quantum states. Hope you have understood the basics introduction of molecular spectroscopy. Now we will discuss in detail, one by one, the rotational spectroscopy, vibrational spectroscopy, and electronic spectroscopy. Let's start with the molecular rotation in diatomic molecules. Consider a diatomic molecule having mass, m1 and m2 separated by a distance r. An molecule is rotating about the axis of its center of mass. The moment of inertia of molecule can be presented as where mu is the reduced mass of the diatomic system. If an electromagnetic radiation interacts with the molecules having permanent dipole moment, interacts with the electromagnetic radiation, because the electric field of electromagnetic wave exert a torque on electric dipole of the molecule. This causes change in molecular rotation. An molecule goes to its excited states by absorbing the energy from incident radiation. In order to understand the transition between rotational states, we first have to know about the possible molecular rotational states in the molecules. Considering the three-dimensional degree of freedom, the classical rotational energy can be written in terms of moment of inertia and the angular frequency of rotation. The angular moment of the molecule can be written as L equals I omega. We can also write the energy of the molecule in terms of angular momentum and moment of inertia. In order to find the rotational quantum energy states, we apply Hamiltonian operator to energy expression and solve the Schrödinger equation, which ends with energy eigenvalues as where J is the rotational quantum number. We can also write the energy expression in terms of wave number for rigid as well as non-rigid rotor. Rigid rotor are those rotor whose internuclear separation does not change during rotation. This is the approximate case taken some time to solve the big equations. Whereas, the non-rigid rotor are those rotor whose internuclear separation changes during rotation due to centrifugal force, which really happens during the rotation. The constant B and D in the above equation are rotational constant, and centrifugal distortion constant, respectively. Here you see the expression for the rigid and non-rigid rotor. If you plot the energy level diagram for the rigid rotor for different values of J, you get this plot. If electromagnetic radiation with energy sufficient for rotational transitions is incident on the system, molecules show transition to exited rotational states, in accordance with the selection rule, delta J equals plus minus 1. If we see the spectrum of these transition, we observe equispace lines at a difference of 2b centimeter inverse. If you plot the energy level diagram for the non-rigid rotor for different values of J, you get this plot. We see in this case the energy level is lower than that of rigid rotor case. This is due to additional term, responsible for the centrifugal distortion. In this case, instead of getting equispace lines in the spectrum, the distance between the line go on decreasing at higher wave numbers. Let's consider the case of polyatomic molecules. The rotational spectra of molecules can be classified according to their principal moments of inertia, Ia, Ib and Ic. It is a convention that the moment of inertia are arranged from higher to lower values. the particular pattern of energy levels, and hence the transitions in the rotational spectrum for a molecule is determined by its symmetry. Based on the symmetry of their structure, the molecules are divided into 4 different classes. Linear molecules. The linear molecules are those molecules whose principal moment of inertias are as follows. The example of linear molecules are HCN and CO2, symmetric top molecules. Symmetric top molecule can be of 2 types depending upon the following condition of principal moment of inertia, that are, oblate or prolate. The example of oblate molecule is BF3. The example of prolate molecule is CH3Cl. Spherical top molecule. Spherical top molecule are those molecule whose principal moment of inertia are as follows. The example of spherical top molecule is methane. Asymmetrical top molecule. Asymmetrical top molecule are those molecule whose principal moment of inertia are as follows. The example of asymmetrical top molecule is water. For details of molecular spectra of arising due to polyatomic molecules, please read the suggested books.